Material properties are the heart of mechanical design, whether it's the material's yield strength or ultimate tensile strength or its ductility. These are the properties by which we evaluate if a design is safe or unsafe, if a design will succeed or fail. In order to acquire those properties, we need to do experiments. And so most often what we'll do is we'll design a tensile sample. We'll subject it to a fixed displacement rate, and we'll record the force that builds up into that part until it fails. Now, at that point, we have force data, we have displacement data over time, and force and displacement are very valuable parameters. It's great to know the brake force, but they're specific to the geometry. If we were to create a part that's way bigger or way smaller, the force required to brake it would change. And so to normalize that, to account for changes in the size of parts, we convert force and displacement into quantities called stress and strain. Now here we're going to start with engineering stress and strain, which is in reference to the initial shape of our geometry, its initial cross-sectional area, its initial length. That's the reference frame that we start with. Engineering stress, or sigma, is equal to the force that's applied to the body divided by its initial cross-sectional area. Engineering strain is equal to the change in length, so the current length minus the initial length, the change in length, divided by the initial length. In both cases, our reference frame, whether it's the area or length, are with respect to the initial shape of our geometry. Once we've taken that force and displacement history and calculated our stresses and strains, we end up with what is called a stress-strain curve. Now, depending on our material and its behavior, we can have a ductile stress-strain curve, where our material has a lot of plastic deformation, it stretches a lot. Or we can have a brittle stress-strain curve, where once our material reaches its peak stress, it fractures with very little displacement, very little ductility, right? Now, what we'll find with brittle materials is that they tend to have what's called tensile compressive asymmetry. What that means is they are way stronger in compression when we're trying to squeeze them together than when we're trying to pull them apart. And a classic example of that is concrete. Concrete is a material that under compression can sustain massive loads. But if we try to take concrete and put it in tension, it will fracture brittle. Very brittle, very little displacement, lots of fracture, right? So now that we've got this idea in hand, now let's go and look at our engineering stress-strain curve and note what are some properties that we can find in this curve. The first property that we can find is what we call as the Young's modulus. This is the slope of the elastic region of our curve, the area where if we were to stretch our part up to a certain amount of stress and then we unloaded it, our part would return to its original shape. That slope that we see in that linear region is Young's modulus. Now, as we get higher and higher in stress, we reach what is called the proportional limit, PL. This is where our curve is no longer linear. It starts to have a change in slope. Now, once we reach the elastic limit, that is the actual point where if we load our part further at stresses higher than that, it won't fully recover back to its original shape. It's going to have some degree of plastic deformation. In order to try to be consistent, because materials that have the curves are very different, we introduce what's called the yield strength, or more specifically, the 0.2% offset yield strength. And this point is where we fully declare for all materials that above this value, plastic deformation is occurring. We are no longer elastic. We are deforming permanently. And that is set by literally taking the slope, E, the Young's modulus, offsetting it, and then plotting a line up from 0.2% strain on the x-intercept up to where that line, that straight line, intercepts the data, right? Now, once we're past the yield strength, our part is plastically deforming. Any strain that we are adding is a permanent change in shape of our part. And we will eventually, we'll start to harden, we can become more resistant to further strain until we get to a critical value of stress. This is called the ultimate tensile strength, SU or SUT, or even SUTS, depending on where you are in the textbook. This is the maximum stress that our part can sustain. And if we reach this value, we can say that our part has failed. Because beyond that value, stress decreases. Our part necks down and tears and deforms significantly until we get to our fracture strength, at which our part snaps, load drops to zero, and our part has failed. Now, if we plot a straight line down from our fracture strength, then we get what is called the ductility of our material. How much overall can it deform before it fails? Now, in this case, we've been looking at the ductile curve, but the brittle curve, because we don't have a lot of plastic deformation, is much simpler. In this curve, the ultimate tensile strength and the fracture strength are one and the same, and there's very little ductility. It's not much hardening, if any, that we see in brittle materials. Now, we've talked a lot about, and we've looked at the stress strain curve in terms of engineering stress and strain, but there's also another way to calculate stress and strain in terms of the true values of stress and strain. This is in reference to the current shape or the actual shape of our part at every instant as we pull it apart. So rather than looking at the area of the initial area, we're actually looking at the area as it necks down and becomes smaller and smaller at higher and higher loads. Here, true stress, sigma t, is equal to the force over the current, the actual cross-sectional area in our part, and true strain, eta t, is equal to the natural log of the current length over the initial length. When we do these calculations and we account for how area is constantly decreasing, instead of having a critical stress of the ultimate tensile strength, instead we see that stress continuously increases as our part necks down and higher force and smaller area until we get to a true fracture strength of our material, which is massively higher than what we found in engineering. And similarly, the true ductility is much higher as well compared to engineering. Now, there are other interesting things that we can do when we think about the stress and strain response of materials. One thing we can think about is that once we get past the yield strength of a material, once we get past yield, that we start to permanently plastically deform our material. But also that as we go up, our yield strength is moving with us. So that if we were to say load past yield, unload, and reload, in order to yield again, we have to go back to where we stopped. So our yield strength increases. We can actually take advantage of this phenomenon to cold work parts and materials to actually plastically deform them so our yield strength is higher in our part when we put it into service rather than having a lower yield strength. Another interesting phenomenon we see in stress strain response is the cyclic behavior of materials when we actually apply loads repeatedly over and over as cycles, loads that, say, are below the ultimate tensile strength. In those cases, as we cycle loads, say under strain control from a certain amount of strain in positive to a certain amount of strain in negative, we start to create what are called hysteresis loops. Loops that represent how stress and strains history evolves cycle over cycle. And we'll see in materials that some of them cyclically harden. So cycle over cycle, they get stronger. They have more resistance to plastic deformation or to deformation in general. Or we'll find some materials soften that cycle over cycle, the 1, 2, 3, 10, 1,000, a million, that they start to soften. They are less resistant, less stress to get the same amount of strain. We also can find in some materials that they have an asymmetry in their yield behavior. That if you were to say, go through yield and tension first, and then you come around in compression, it will yield at lower stresses in compression because the whole yield surface has shifted. That your material, because of all that cold working you did in tension, is less resilient in compression, right? Now, in order to engineer some of these behaviors, cyclic softening and hardening and Bossinger's effect, what we need to do is engineer the microstructure of our materials to change the grain boundaries and precipitate phases and particles, the material science, the hidden features behind which the bulk properties come from. And there are three key ways that we can do that. One thing we can do is to quench our, say, steels. This is where we take them above their austenizing temperature and then quickly cool them down, causing a phase change from austenite into martensite, creating a very hard material, but with high internal stresses. Another thing we can do is temper our materials. So after we do a quench step, we can take them to a temping temperature, hold for a period of time to relieve those stresses, make our part more ductile. We lose a little bit of the strength from the quench, but we end up with kind of a balanced set of properties. And then finally, another process we can use is annealing. This is where we take our material way up above its recrystallization temperature, where its grains can start to soften and new grains can start to grow in its microstructure. And then we slowly cool it down, allowing it to form a permanent microstructure that is very different from a quench. By balancing these different types of heat treatments, we can engineer our microstructure to be very ductile, to have a lot of tensile strength, or to have a high yield strength, or combinations of them all. Now, materials are not just metals. There are many different classes of materials we need to consider. Of course, metals are our standard structural materials and we use often, but often we may want to use a polymer if we need something that's lightweight, that doesn't need a lot of strength, or elastomers if we need something that has a lot of ability to stretch and recover, viscoelastic materials or dampers. We could use glasses where we need things that are transparent, or ceramics where we need thermal insulators. And often in aerospace engineering, we use hybrids. We create composite materials that blend high strength and low weight ratios. Now, in terms of selecting a material for a design, there are many things to consider. A design isn't just its tensile strength or its yield strength or its ductility, but it's also things like, can a design be repaired? Is it a material that can be repaired and welded? Does a material have good thermal properties? Can it conduct heat away? Is it resistant to crack growth, or does it have a low density? So the reality of design is that there are a spider plot of properties in any material, and we need to figure out for our design what's most important. Which of these properties do we need to make sure that our design won't fail? And what's the balance between them? Should I use this alloy A, or should I use alloy B, and why? Now, to help us make selections between various properties, there are things called Ashby plots. And these are plots where we take two or more properties and compare them to each other for different classes of materials. For example, we can create a specific modulus plot, which is Young's modulus over the density of a material. And we can use that to try to minimize the weight of a part while dealing with things like how much it deflects or its stiffness or the natural frequencies, how it vibrates under dynamic loads. We also could create a plot of something like, say, the specific strength, which is the strength or the ultimate strength of a material versus density. And again, we can use that to try to minimize the weight of a part while making sure that we meet our required strength for a design, that our design is strong enough to survive while it's as lightweight as possible. Now, how do we gather our material properties? There are four principal ways that we can choose in descending order to get material properties. The best way, the most critical way, the way that you should do it, is perform your own experiments on the specific material of interest under the environmental conditions that your design will be subject to. So, say you're going to buy some steel from a certain foundry in Canada, that's going to be your key supplier. You need to get that steel. And say your steel in the actual design is going to be subject to 300 degrees Celsius. That's the design is going to be at that hot, and it's going to be in an inert environment. Then you need to design a test on your specific steel at 300 degrees in an inert environment so you can capture the real or the best properties that represent what your design will see. Whenever possible, you should do this, right? However, performing experiments is costly. And if your environment is, say, a nuclear reactor, it can be kind of challenging to run many tests in a high affluence in a radioactive environment. That's not easy. And so there are other methods that we can try to do to estimate our properties. One of them is to use softwares and handbooks. Finite element softwares that we use to simulate our parts and the stresses that they have in them often come with built-in databases for known materials. So these can be like curated data that people have done many experiments on that are shared with you so you can quickly try to iterate a design. These are usually are well cited. You can trust that data, or they're at least traceable to what source it came from. And a great example is in ANSYS. There's ANSYS Granta Selector, which has a lot of data. Another option is to use material property handbooks. There are various engineering organizations that have collected a library of material property data for many different classes of materials and conditions. These handbooks are very expensive, but they're very useful as a design engineer. Some examples are the ASM handbook or the military handbook for materials, the MMPDS, which is used to design military aircraft and civilian aircraft. And then also there's the composite materials handbook for designing composite structures. All of these are very good tools, qualified tools that you can use to design structures. Now, there are two more options that we have for material properties. Not very good options. So I'll give you that. These are not great options, but these are options if we're just trying to get an initial design with plans to go and do our own experiments. One of them is to go and search scientific papers, to search peer-reviewed journal articles or peer-reviewed conference papers to see if there are property data, if there's property data shared by academics, by researchers. You can go read those papers, contact the authors, and request a copy of their data if they deem to share it. The final and the least useful, the highest risk approach is to simply try to estimate our material properties. This would be to say, hey, I have a certain class of steel it's similar to these other steels. So let me just assume that it's somewhere in between steel A and steel B. Its properties are somewhere there, ballpark. That process of estimation is the highest risk for design. And I do not recommend to use that just straight up estimation process unless it's for an initial design with plans for you to conduct experiments or for you to search databases. Overall, there is no better method than to acquire your specific material, to design a test that mirrors its actual environment and run many of those tests so you actually know the properties of your material.